have the feeling that a diverse group of students like that is going to agree on another time.
How long is it going to be?
Hour, 15 minutes, hour and a half.
Not till midnight?
If you'd like to, but then I have to add more problems. So if you like, we can make it long. Now, again, the level of the test is certainly going to be easier than the problems that I am giving you as homework. The idea about the homework is to really make you think about unusual problems that you may encounter routinely in your experience. So the test is going to be more some reworking of the things that we have studied already on a simpler level. Of course, you have to figure out a few things. You have to know how to apply the formula, and you have to make sure that the dimensions don't get wrong, so you don't get strange answers. Apart from that, again, the idea about the test is not to get you, or the homework for that matter. It is to give you exercise. We're not going to, the grading is going to be rescaled depending on the best grades rather than depending on how many problems you have solved. So don't think about grades, think about understanding these things and being able to apply them. Something related to the homework, you have had this problem with Israelashvili. I had a constant stream of people coming in my office today, where you have these two particles being in touch and then being separated by a surfactant layer, by a couple of surfactant layers. Now, there are two very simple keys to that problem, and it immediately gets to be very simple. But just as a reminder, first you have two particles in touch. Now, the formulas for van der Waals attraction always have the distance between the surfaces of the particles on the bottom. So you have to put some distance, otherwise you get strangely divergent formulas. In order to avoid that, you have to put some distance, which would be what? The typical distance between molecular layers in adhesion. And I have given you this distance, which is on the order of 0.2 nanometers in the lectures, actually. Sorry that Israelashvili hasn't mentioned that, but I mean, again, as an idea, you have two particles or surfaces in touch. The distance between them is not zero, because this means that the molecules are going to overlap. The distance between them is the distance between two molecular layers in a crystal or material, which is on the order of 0.2 nanometers. Second, you have a layer of surfactant around, which is with matched refractive index. If you remember, on the lectures we discussed what is matched refractive index in terms of Hamaker constant. This means that if you match the refractive index of something that's immersed in media, you are going to have the same Hamaker constant as the media. So when you separate two particles with a layer of that surfactant, you are essentially separating them with a media which is equivalent to the solvent, to the suspension media. So you just have to calculate the force between the particles some distance away. And because you know what the ratio of the two should be, you don't need the Hamaker constant even. You just have to find the ratio related to the ratio of distance between the particles. Any questions about the homework, the test? Any other problems for that matter?
The solution sets were emailed out to us.
Right.
But print them out and you can barely read it. All the handwritten things you can barely make out.
Yeah, I guess some of them may not have been scanned that well. I have them on a hard copy, and if you drop by my office, you can make a copy. I may try sending some solution sets to you tomorrow. I'm certainly going to send the solutions for the last homework to you tomorrow by email. Sorry that we don't post them on the web page, but we have some of the distance students have been delayed because of the CDs that they have to receive and so on. So we just have to send them by email for now. I'm going to send you the solution for this set of homework, the last set of homework tomorrow. And any other solutions, previous solution which you have problems with, you can come to my office or Daniel's office, and you can get the solutions from them. I'll ask Daniel actually to help you if you know which specific pages you want.
Yeah, if you bring a disk, I'd be happy to make copies for you.
Anything else?
Also, we haven't received solutions for problems at 3 and 4, homework 3 and 4. We've got 2 and 5.
That's because she forgot to mail in one of the homeworks. Right? She spread it up in 3 sets. She
Uh-huh.
mailed 2 sets and forgot to mail 1 set.
Okay, Daniel, please just check out which sets have been sent or not,
Like the first two.
and please take care of that tomorrow. If you have any other questions about the test, I'll be in my office, about the problems and so on, I'll be in my office tomorrow afternoon, on Thursday during the office hours. Daniel is going to be in his office during his office hours tomorrow. So drop by and ask. If you know the lectures and the formulas well enough, you should be able to solve the test without much problems. Just figuring out, however, a few things here and there. Which works in which direction, which type of formula we should use and so on. But apart from that, it shouldn't be difficult. Okay, so let's get on with this lecture. Now we know everything about van der Waals, everything that we need, that you would like to know, and possibly some of the things that you wouldn't like to know. But if your knowledge of colloid science is restricted to that, then you would know why things can flocculate and form precipitate, but you wouldn't know why things stay suspended and why we are as we are, kind of in this constantly stable state, although metastable state, in fact. So we have to study the next second big, large colloid type of forces, and this is electrostatic forces. So what we're going to do this time is we're going to go through the basics, all the formulas that you have to know about electrostatics before you can calculate the forces. Again, I'm going to show the derivations schematically. This is not something that you should immediately try to understand. Actually, one of your homework problems is to repeat some of the derivations in this case. But what's important is to get the physics of what's going on here and why does it happen in this way. And starting with the unusual, interesting picture shown here. Now this is a colloidal crystal from latex particles, latex microspheres. This is a research which has been going on for quite some time of these specific types of crystals. Now this is not a photonic type of crystals, and we're going to discuss this a little bit later. Now what you see here, you can see the particles as bright spots. And what you can see is all those particles, which are so large that you can see them on the microscopes, are actually at quite far distance from each other. And you can see that they're actually in crystallized state. So obviously they don't want to get to each other, and they would like to organize so they can be as far away from each other as possible. Now the way to make such suspensions is to take latex suspension, which typically doesn't form this structure, and then deionize the suspension, remove the electrolyte, which is a long and tedious process, which can take a period of days to weeks to months and to years. There is a Japanese piece of research where they showed data on similar systems which have been deionized for 3 years, which can be a good graduate project, right? I mean, you load your samples in the first year, and then you have some time. But the point is, why by deionization, removing the ions out of this system, you can get this far away repulsion. What is the origin of the repulsion? I guess you're already, guessing that. Now, why would deionizing be the key to making these long-range structures? Now, could somebody make a suggestion on that, or shall we go directly to the explanation?
It shields the effect.
Sorry?
It shields the ions in the solution. They basically shield the effect of charges present on the.
Okay, so then you're going to tell me that when you remove the electrolyte, you're going to unshield the effect. This is conceptually true, but factually it is not quite true. And we're going to, discuss, this is what we're going to discuss in this lecture, actually. So one of the major reasons is understanding how these things work. And this is not immediately, you know what electrostatics are, but this is not immediately visible in the case of colloid systems, and this gives a very big degree of control of the system. So we're going to discuss this a little bit later, but for now you know that unlike van der Waals forces, electrostatic forces can be very important, and they can be very long-ranged. You can see that we're speaking about micrometer distances here. From the viewpoint of van der Waals forces, micrometer distances are something that's worlds apart, something that really doesn't matter too much. So all the concepts that we're going to study essentially boil down to, give one more try here, no, essentially boil down to having a surface and having charges on the surface. Now, nothing in a closed liquid system would have permanent charge, in the sense that you cannot have an excess of electrons or positive particles in a certain system. The overall system is going to be electroneutral. Otherwise, if you have two systems like that, when you connect a wire, there's going to be current flowing. So if you're going to have ions on the surface, you're going to have ions in solution too. These ions are going to have opposite charge, and the common terminology for this type of ions is called counter ions. Because the counter ions would be in a free state, they're going to be free to move around, diffuse closer or further away from the electrode. And this is something that's very important when it comes to colloidal science and interactions. Before we go to the derivation of formula and to even understanding what happens, now what is the origin of the charge? Here is a summary of the three hypotheses which you can apply to any colloidal system, and you are likely to find out that this is what we have in the real system. Now, the first and simplest case would be you have surface charge groups. No group comes charged in chemistry in its original state, so we're going to have a group which is going to be ionized. In this case, you have COOH carboxylic groups which may get deionized, which may get ionized at high pH and deionized at low pH, so you can even control the charge. The point is that if you have COOH group on the surface is going to obtain CO minus charges, and then there would be protons released by the surface. You can also have the opposite case, where the surface releases negatively charged groups, and in this case the charge on the surface is going to be positive. The example that I have shown here uses OH minus ions, but typically, if you remember with surfactants, the positive charges usually come from amine groups. Now, in order to have such types of materials, you need to synthesize particles which have the surface chargeable groups. In many cases, however, just simple substances are going to have to acquire charge. And this charge is going to come because of preferential solubility of some of their chemical components. What is shown here is the two cases where we have a crystal of silver iodide. Silver iodide is not very soluble, so you can have crystals of silver iodide in suspension. Now, both the silver and the iodine ions would like to dissolve. They're going to have some small solubility. The question is which of them is going to dissolve more. If one of them dissolves more, then the rest, what remains, is going to be the oppositely charged ion on the surface. So the crystal itself is going to acquire a specific charge. One way to control this charge actually would be to control the ionic composition of the environment. So you can control this type of charge by pH, for example. You can control this charge by controlling the ionic composition. So you have silver iodide. If you put in potassium iodide, out of these two ions, you are increasing the concentration of the iodine ion in the solution, which means that it's actually going to be the silver ion which is going to dissolve because you have already saturated the system with lots of iodine ions. So your silver iodide crystals are going to acquire negative charges on the surface because there will be less iodine ions released from the crystal than silver ions. Oppositely, you can put in silver nitrate in the solution. You're going to have an excess of silver ions. So the ions that would dissolve preferentially are going to be the iodine ions. And your silver iodide crystal is going to be positively charged. And one very important practical case shown here in the third image. You may have a neutral surface, hydrocarbon, plastic, without charges, but you may charge it by absorbing certain substances from this. The simplest substance that you can absorb is what? Surfactant. If you have hydrophobic surfaces and you put in a surfactant, the surfactant will absorb on the hydrophobic surfaces. Then the charge group of the surfactant is going to face the water. So the surface is going to acquire charge. And this is the case here. RNH3+, for example, this will be what type of surfactant? Sorry? Yeah, right. No. I mean, like just in general terminology, I'm kind of just a little bit of revision. What types of surfactants do you have? Right. This is what? This is cationic, obviously, yeah. Or you can put anionic surfactant, and it's going to charge the surface negatively. You need not absorb surfactants only to change the properties of surfaces. Actually, as part of my graduate research, I have studied the absorption of hydroxyl ions on surfaces. For some reason, which is not quite understandable yet, the OH minus ions would like to absorb on hydrophobic surfaces. And so any hydrophobic surface in water is going to have some negative charge, which comes just because the OH minus ions from the solution absorb on the hydrophobic surface. So in many cases, the charge may be acquired just because you put the substance in the solution, it releases some ions, it absorbs some ions, and so on. You're going to have a charge, whether you like it or not, with all consequences about electrostatic repulsion and so on. Typically, you would like to have charge because you would like to have stable colloidal systems. Okay, so any questions about charging, all those reactions or similar?
What is the isoelectronic point?
Isoelectric point.
Electric, is that related to that?
Yes, we're going to come to this a little bit later. It's typical when you have surfaces which can be both negative and positive. The isoelectric point will be the point at which the surface has zero charge. And this is going to have zero charge because at low pH the surface is going to be positively charged. At high pH the surface is going to be negatively charged. In the pH right in the middle you're going to have zero charge. And you're not going to have electrostatic repulsion, and you're going to have your system eventually coagulating and precipitating. This is very important when you have biomolecules, proteins, DNA, and similar. Any biomolecule in suspension would greatly change its charge depending on pH. So I'm going to address this issue a little bit later specifically for biomolecules. And now comes the tricky part. Now, why the surfaces, and this is what you have to remember from these lectures. If you remember the formulas, but you don't understand this physical point here, I mean, you're not going to benefit. On the other hand, even if you don't remember the formulas, just understanding how this works is going to be important. So let's discuss now, why do you have electrostatic repulsion in the first place? So let's consider some physical models about that. Now we have these two surfaces which I showed on the previous slide. Now can you say that this is the model which you have? You have two negatively charged surfaces some distance apart, and because they have the same charge they repel each other. Does this look like something that's true and that's going to work? Hmm? Sorry? Well, this is just two surfaces, so like we have two two surfaces, let's say any distance. I mean, what we're thinking here is how we're going to calculate. Now, we don't know, for example, that people have been calculating this before us. So we decide to rediscover colloidal science, and we want to develop formulas for calculating the repulsion. So the question is, what types of formulas are we going to develop? So can we start with a model which just assumes that we have two charged surfaces which repel each other and do electrostatics? I see that you say no, nay, which would be, why would this not be right?
There's a vacuum in between.
Right, so somehow in this model, which would be electrostatic model, somehow we forgot to put in the ions, right? If you take a look here, in all those cases you release ions. You release opposite charges. Now then we can't calculate electrostatics by just assuming that we have repulsion between electrostatically charged surfaces, because we forgot about the charges, and the charges are there. And this is very important. So the electrostatics in colloid science are not the electrostatics in physics. In physics, you know that two oppositely charged bodies repel each other. In colloid science, you can't say, well, these particles repel each other because they are charged. It's not that simple, because they may be charged, but they have ions. So then we scrap this model because it's physically wrong. And then let's consider two surfaces which are, now the distance is important already, which are long distance apart. And these surfaces have released counter ions, and they interact. And we say, okay, now maybe we can do electrostatics between symbol surfaces, but maybe we can do electrostatics between surfaces which are releasing ions. So maybe we can start just calculating the electrostatic interaction between all the ions and all surface groups in the system. Now, is this going to work in this way, as an electrostatic model?
You need to know the density of the pluses, I think.
That's a good point. That's when you go do the model. But let me put the question this way. Now, you are situated here around this ion, and you want to calculate the repulsion between this ion and all positive and negative ions on the other surface. You have lots of ions. Now, what's going to be the negative interaction with this ion with all the charges and counter ions on the other surface?
Zero.
Right. Exactly. Because this surface, as well as the other one, is electroneutral if you take a look from long distance apart. So the bottom line here is that if you just think again in terms of electrostatics but include the ions, you are getting zero force. So the origin of the repulsion is in a way not electrostatic at all, even though it's caused by electrostatic effects. And the origin of the repulsion would come from something else, and I have given you the clue here. Now imagine that you bring those two surfaces closer together. So the ions start overlapping. Suddenly what you're going to have is increased concentration of ions here in the gap between the electrodes. And you know from thermodynamics that whenever you increase the concentration of something, you have an osmotic pressure, which is the equivalent of a strong, it can be repulsive type of pressure, or it takes lots of energy actually to create some osmotic pressure effects and so on. So the bottom line is that all the effects that we're going to study here are actually can be equilibrated, attributed to osmotic effects, in the sense that it is the overlap of the atmospheres that actually creates the repulsion rather than electrostatics itself. On the other hand, however, you cannot do all those calculations without understanding electrostatics and how it works. So by the end of this lecture, we're going to know everything that we have to know about electrostatics. So in the next lecture, we can directly apply those formulas to very important cases and immediately understand the behavior of a variety of colloidal systems. Kind of fill up most of the gaps that we need to know about colloidal suspensions, for example. However, before we do that, we have to swallow some formulas here which begin easily. And the first thing that we have to consider is where are going to be the oppositely charged ions, the counter ions, with respect to the surface. Now the surface is going to release them, but are they likely to run far away from the surface? Not, because they are attracted. They are oppositely charged and they would like to be close there. On the other hand, you know that every time you have an attractive force, the thermal motion also tries to spread out the particles or the ions and so on. And you know, if you remember, we had this slide with a vertical cylinder and how the particles are going to stack up vertically. You know that if you take the chemical potential, which in this case is going to include the concentration term and the charge term, you can immediately integrate this with respect to the density. So the density at any point is going to be some zero density, some calibrating density, times the exponent of the electrostatic energy divided by the thermal energy. Now, Z is the charge of the ions. +1, -1, +2, -2, and so on. E is the charge of a single electron, a constant. And psi is the electric potential. Z times E times psi gives you the electrostatic energy of an ion. So what you have here is the Boltzmann distribution in the case of electrostatics. Tells you that the ions will be distributed against the field that attracts them to the surface. If you know what is the dependence of the electrostatic energy as a distance, you are going to know the distribution of the ions away from the surface. So this in itself is not a good closure for your problem. The problem here is that you don't know what is the dependence of psi, of the potential, as a function of this distance here, the coordinate x. You can actually draw pretty well with the mouse in some cases. Okay. So anyway, you don't know what is the potential of psi as a function of x. Yes?
The ions want to align on the right up against the plate there, the negatively charged plate. When you show kind of a random distribution of the ions, is the
well,
ions
the causes that they're going to be are they're going to be just one ionic distance away from the plate, from the plane.
Be a potential energy minimum eventually in this
Right.
system?
That's where they're going to put their potential energy minimum. And this is important to the extent that some models of how the ions actually, we're going to just discuss this a little bit later, perhaps, when you do electroosmotic effects. But some people go even to the extreme to consider actually two layers here. One layer where the ions are just against the wall and just sitting there, and one layer where the ions are diffusely distributed. So people have done actually models for the capacitance, for the distribution of the ions and so on. And some people thinking exactly along the lines, these lines, have considered the first layer of ions can be considered as something that's fixed, immobilized. But there is always going to be there are always going to be ions which are going to be diffused, which are going to diffuse around because of the thermal motion. And as we're going to see, it is the ions which actually diffuse out, which make all the electrostatic effects possible, because these are the ions which overlap. But apart from that, there are models which exactly say that there is going to be a plane of ions. So the ions are going to be mostly around here, and I'm actually going to give you an estimate how mostly. But then there are going to be some diffuse ions. Now, in order to understand that, however, you can see that if you study the field here, let's say you start at a very high field. But then as you go through the ionic layer, this field is going to decrease because you go through more and more positive charges. And this field is actually going to go to zero if you go very, very far away from the surface. So what we are discussing here is just, we don't have any more. We're going to discuss the case where we have additional ions later, but right now we have just a surface with the ions which are released from the surface, nothing else.
Just one other question then. If the chemical potential is dependent upon the electric potential, how can you distinguish this repulsion force as an osmotic repulsion rather than electrostatic?
This is another good question. I mean, you're almost ready to teach this course. No, the point is like that. I mean, people actually have done the same calculation by using electrostatics, but then the osmotic effects have to be included in the distribution of the ions. So you can calculate the electrostatic contribution, but just because the ions would redistribute osmotically, and this is going to create some additional electrostatic force actually. Or you can calculate the distribution of the ions, and then assuming that there is an overlap of the ions, then you can calculate the repulsion osmotically. So it's whether you choose to work with osmotic effects or electrostatic effects, they really kind of in a way can be replaced. From the viewpoint of colloids, however, it's very instructive to think in terms of osmotic effects, just because you're going to see that, I mean, this is a very simple way to calculate that. Now, we have the potential here which decreases. So one equation which just tells you how the ions are distributed is not enough, because the ions would not be distributed at an even potential. So an ion here, for example, is going to experience almost zero potential because the potential has decayed already. An ion here doesn't see the negative surface, it sees positive charge ions. So we need one more equation which relates actually the potential, the distance, and the distribution of the ions. And this is the so-called Poisson-Boltzmann equation. So essentially you start with the Poisson equation, which tells you that the distribution of the potential as a function of the distance is going to be a function of the charges in the media. Now we know the Boltzmann distribution, so we can plug in this one here. And we have the Poisson-Boltzmann equation, which relates the potential, the distance, and the distribution of the charges away from the surface. So if you can solve this equation here, you can solve all electrostatic effects in the system. Now the question is that this equation, as you can see, is not a very straightforward one, because you have the potential here and here. It's non-linear, but the problem is that this affects the potential also appears in this distribution, so it's kind of a system which you need to break open and solve by using some approximations. Unless you would like to do lots of numerical calculations, which some people do, of course. Okay, so we know these equations. Now we have these basic equations, and from here on we can immediately start obtaining some information about the system. If we want to solve a system of differential equations, we have to know the boundary conditions. Now, this is the system that we are studying, two surfaces with ions released from the surface. The potential the ionic distribution is like that, the potential is like this. The point here is if the surfaces have the same charge, then the first derivative of the potential with respect to the distance right in the middle here is going to be 0. This is one of your boundary conditions. The second boundary condition is going to be like that. If you take half of the system, the number of ions which you're going to have in this half of the system is going to be equal to the surface charge. So then you can say, okay, the number of ions, now sigma, which is the number of surface charges, surface charge per unit area, is going to be equal to the integral of the distribution of the ions times their charge from this plane here, d over 2, d is the distance between the plates, to the midplane. So then you can put in here, you know that this is the left-hand side of the Poisson equation. You can replace it with the right-hand side of the Poisson equation. You can do the integration where you have from a second derivative, you go to a first derivative. So you now know that the surface charge is going to be equal to the electric permittivity of the media times the first derivative of the potential with respect to the distance, which is equal to, Ketan is going to tell us what the first derivative of the potential is. Huh? The field, right. So the first derivative of the potential is the called electrical field strength. So right now you have obtained immediately a very simple relation between the field strength, the surface charge, and the electric permittivity. You can actually see how the dielectric permittivity affects the field strength. The higher the dielectric permittivity, the lower the field strength at the same surface charge. Now, before questions, one thing that you need to pay attention in all those electrostatics problems, particularly when you take a book like Izraelashvili, it's a very good book, but still explaining this is difficult. Pay attention where the origin of the coordinate system is. Now, the origin here is in the middle, and the coordinate system goes from minus d over 2 to plus d over 2, where d is the distance. At some point later, Izraelashvili changes the origin, placing it on the surface where you have a single surface. In order to understand the single surface, you have put the origin on the surface. So you have to pay attention. In the first part of the derivation, 0 is in the midplane, in the middle between the plates. In the second part of the derivations, where you have surface with electrolyte, 0 is actually on the surface. So just pay attention which is surface, which is middle between the plates. Okay, any questions about this slide? So far so good, just deriving formulas. Then we can keep on deriving formulas. Now this looks scary, but the result is very important and actually simple. Until you follow the derivations, actually they are pretty straightforward. Now we want to know the distribution of the ions as a function of the distance. And in order to do that, it is very instructive to find the derivative of the ionic concentration as a function of the distance. We can take the Boltzmann distribution, and we can take the derivative with respect to the distance. And we have here this derivative of the potential with respect to distance. Now here we have something which is actually very similar to the Boltzmann distribution itself, and because the Boltzmann distribution also appears in the Poisson-Boltzmann equation, we can actually substitute this term with the derivatives from the Poisson-Boltzmann equation like that. So then you obtain a relation between the derivative of the ionic distribution as a function of the distance and all those complex sets of derivatives here, which, if you do some math, is going to be equal to this term, which is permittivity, kT, and the derivative with respect to distance of the squared first derivative of the potential. Now this looks kind of weird. It's really mathematical formalism, so there are two questions here. Now first of all, how did we come from this formula to that formula? If you don't believe me that this is equal to that, what I would suggest is you can actually start with this and do the differentiation here by following just the rules of differentiation from the algebraic books. And you're going to see that actually you're going to arrive at this expression here. What people now, why are you happy with that? Because right now this derivative is the field. So right now we can use this derivative in order to obtain a useful relation. We put in, let's say we take the integral of the ionic concentration from the midplane to the surface. The difference between the ionic concentration on the surface and the ionic concentration in the midplane is going this integral from here to here of the derivative of the density. We know what derivative is this, so we plug in this formula here. We have this differential with respect to x, which immediately disappears. So we have eventually an integral over the d psi dx, the derivative of the potential. This integral immediately cancels here, so we end up with the formula which gives you the relation between the difference in the ionic concentrations and the first derivative of the potential, and this one is equal also to the field. So what we have obtained here, just kind of forget which comes from where, just take a look at the formula here. We have to obtain the relation between the concentration of the ions on the surface, the concentration of the ions in the middle, and the field strength, plus a few parameters. We have already obtained the relation between the field strength and the surface charge. So we can also use the same relation in terms of surface charge. This is something very important which is going to emerge from this formula. We're going to use it over and over in the derivation so far. The point is that we have derived this very useful formula for the surface concentration, bulk concentration, first derivative of potential, which is field. It's just a useful formula. But you can guess what it's going to be useful for, because we can calculate the concentration of the ions in the middle, and then maybe we can calculate the force, which we're going to do next time. Any questions about this so far? Any errors noticed or some place or something like that?
It seems like it's independent of what d is.
Of the distance.
Yeah.
Sure, and that's cute, right? Isn't it? I mean, this is the good thing about these formulas, that you obtain very general useful relations which you're going to use later. Okay. Now, once we have derived this formula, it's always good, if you have any questions, you can ask them here actually. It's always good to check out how it works and how what is going to give you. So, by using this formula, you can say like that. Now, I have an expression for the ionic density in the middle. If the surfaces are at very large distance apart, the ions are going to be close to the surfaces, so there is going to be nothing in the middle. So for a single surface or two surfaces far apart, you know the relation between the ionic density on the surface, the surface charge density, and a few parameters. This is very much related to the questions about this first layer of ions. This gives you the concentration of this first layer of ions close to the surface. And then you say, okay, we want numerical estimates. So what would be the case of water with some typical, not very high surface charge density? Note the dimensions here. Charges per square meter. Surface charge density. So if you just do the calculations for water, you are going to find out that the concentration of the counter ions here is going to be 12 moles. Now, chemists and chemical engineers here now know that 12 moles is a lot. It's so much that if you take some salts, you can't even dissolve 12 moles of salts in water. So you're going to have an enormously high concentration of ions on the surface. And this can immediately tell you why the electrostatic repulsion is going to be so strong. Imagine that you have to push these surfaces through an osmotic pressure of the 12 molar molecular solution. 12 moles of molecules are going to have osmotic pressure which is on the order of tens of atmospheres. And people have done, have solved the formulas. I'm not going to actually solve even the formula for the potential here because we're not going to need it in this case. But people have checked these formulas with exact molecular dynamics modeling and so on. And they have found out actually that all this matches fairly well. This is instructive in the sense that you see here that you have very high surface concentration, but you still see that you have some ions away from the surface. So even though the surfaces are not very close together, you still have the ions overlapping, which means repulsion. Okay, questions so far? Yes.
Now this sort of implies that the electrostatic repulsion is dependent on temperature, and zero temperature there wouldn't be any.
Sure, yes. Yes, but but again, this is not electrostatic repulsion. This is osmotic repulsion. This also gives you the difference between electrostatics and osmotics here. Osmotic repulsion is dependent on temperature. Electrostatic repulsion as such is not. So this also implies that it's osmotic effect. Temperature effect is not very important for electrostatic repulsion because in the range in which you would work in water, it's going to change very little. And the water is going to freeze much below you reach temperatures where the electrostatic repulsion is going to decay. So the temperature dependence here is important fundamentally because it shows that it's not exactly electrostatic repulsion as just repulsion between charges. It's more complex, it has osmotic origins. But that's a very good point. Yes?
So if you brought these surfaces really close together,
Mm-hmm.
and where it starts to come up, and that's the center, would that
Right.
mean that it's always going to be relatively the same concentration from the center to the wall, regardless of how close you bring them?
The concentration in the center is going to, relatively it's going to be the same because the surface concentration actually is going to start increasing too. So they kind of, if you start bringing them closer, this one is going to go up. And this one is going to go up simultaneously with this one. The reason this is going to happen is again the osmotic repulsion between the ions. When these ions repel, more ions go towards the surface and increase the surface concentration there. So the difference between them, I mean, that's a very good point. The difference between them is always the same. The one in the center, however, is going to increase and it's going to lead to higher and higher repulsion. And just to calculate the repulsions, here is how you calculate the repulsions. Now this is mind-boggling calculation in the sense that here you are doing, you're solving this differential equation with respect to the distance, but then you are obtaining a result which is dependent on the, so you're solving it along this coordinate, but you are obtaining a result which is actually dependent on this distance. And Izraelashvili doesn't do a very good job in explaining that. And I don't think it's very easy to explain either. I mean, you can try absorbing this to Izraelashvili. Let me sketch what happens here. I think, however, the end result is very simple and obvious. Physically, you understand what's happened. So you start by solving this equation. Again, you start with the chemical potential. We always start with the chemical potential. Whatever we do, I mean, that's the first thing to do. Now, in this sense, in this case, however, you take the derivative of the chemical potential with respect to distance, which when multiplied by rho is going to give you the dependence of the pressure as a function of the distance. So the derivative of the chemical potential with respect to distance times rho is giving you the derivative of the pressure with respect to distance. This is just basic thermodynamic formula. Now you have to find out how the chemical potential changes. So you take the differential of the chemical potential here, which is the differential of the potential and the differential of the concentration. In the differential for the potential, you put in again, plug in, replace ZE rho with the second derivative from the Poisson equation. You do exactly the same substitution which you did in the previous slide. So you obtain here squared first derivative of the potential. And then you integrate this from, now in this case you change the boundaries of integration. So you actually get the integral of this from a distance of d to infinitely large distance. The kT term, the concentration dependent terms gives you kT times rho at certain separation minus at infinite separations. This term, however, doesn't look like rho, but actually it is. If you take a look at what these derivatives actually bring you from the previous slides, you're going to find out that this one, this is the expression which we derived from the previous slide, written in another way. This difference of rho is actually it can be expressed by the second derivative of the potential. Now all those rhos and all those integration in distance and kind of this coordinate and distance between the plates, finally everything cancels. You get the very simple formula which tells you, and it has a very important physical meaning, it tells you that the pressure between the surfaces is going to be kT times the rho, the ionic concentration in the midplane when the surfaces are at a distance d apart, minus the ionic concentration when the surfaces are at infinity. You can safely assume that this one is 0, of course. So it tells you that the pressure between these two surfaces, the pressure that you have to apply in order to bring them closer, is going to be equal essentially to the osmotic pressure of the ions in the midplane. It doesn't get any simpler than that. So we did, if you don't like all those formulas, you don't kind of have to remember them. All you have to remember is that the osmotic pressure is related to the real pressure that we have to bring the surfaces together. So all you need to know is the ionic concentration in the midplane, and we can calculate electrostatic forces, which we're going to do next time. Yes?
I was just confused on the notation. For at the bottom there, is that the derivative of psi with respect to x, keeping x constant?
Yeah, this would be, actually this one would be here at x at a certain distance d. So x may be constant, but this is actually at a constant. What it implies is d is constant, not x is the constant. So it's a little bit confusing. I myself kind of like, I can follow my way when I read this Rewashvili, but explaining this immediately is a little bit, it's not straightforward. There is also in that derivation, there is also this additional consideration that if you work in terms of chemical potential, the chemical potential is going to be equal all around, and the pressure is going to be equal all around. So actually the pressure here, for example, the osmotic pressure here is going to be equal to the osmotic pressure here. So at some point you replace x with d and so on. So it's, it looks confusing, but that's the way it's just getting derived. This will be at any d, but then at fixed d. So this is essentially the formula that we had in the previous slide. So it's not immediately straightforward. The point, however, is that you need to calculate pressure between surfaces. All you need to know is the concentration of ions in the midplane. And we're not going to do this calculation right now because we have something else important to do by the end of the lecture. And this something very important comes from the following point. Now, the system that we have been discussing so far is useful, but it's not very practical. It's not very feasible. If you have surfaces in water, you are also going to have what? You're going to have ions which come from the dissociation of water, from the absorption of air, and so on. So you are never working with system where the ions are just the ions which are released from the surface. You are always working with a system which has some electrolyte. Not to speak of systems like our bodies, which are full of electrolyte. So everything that happens there is in electrolyte. Now, these formulas were derived without additional electrolyte. Now, what happens when we add electrolyte? So I want to derive a few formulas by the end of this class, which we're going to use next time. So we're starting with a charge system. This charge system, however, has not only counter ions, but it what is called co-ions, or which are ions of the same charge as the ones on the surface. If we have, for example, a positively charged surface, this positively charged surface is going to release negatively charged ions. But if we add sodium chloride, the sodium chloride is going to release both positively and negatively charged ions. The negatively charged ions, both from the surface and from the sodium chloride, are going to be counter ions, and the positively charged ions are going to be co-ions. Now, the counter ions are going to be attracted to the surface. The co-ions are going to be repelled from the surface because it has the same charge. So what we have to do here by the end of this lecture is just understand how their concentration are going to depend on as a distance. So it gets to be simple. Without electrolyte, we have Boltzmann distribution of counter ions. With electrolyte, you're going to have Boltzmann distribution, but this is going to be the Boltzmann distribution not for the counter ions only, but it's going to be for any type of ion which is present in the system. What I have shown here is for the case where we have sodium chloride. Both the concentration of sodium ions and the concentration of chloride ions are going to be following the Boltzmann distribution. The difference here is what? It's a difference of this sign here. And this sign here becomes positive because the charge of the chloride ions is negative. So you're going to have negative Z here. Z is going to be -1. So the charge inverses to plus. And what these two formulas tell you is that the co-ions are going to be repelled, the counter ions are going to be attracted. And now here is the case where we have inversed, okay, we have changed the coordinate system. Now x equals 0 is on the surface, and x equal to infinity is obviously at infinity distance. Now why do you use this coordinate system? Because at infinity, the concentration of all ions is going to be constant. It's not going to be affected by the surface. And this is very important to understand. So there is going to be some difference in the ionic concentration around the surface, but it's not going to spread too much. It's going that at infinity the ionic concentration is going to be even. And from here on, we can also check out what happens to the equation that we derived. Again, I would assume that you would believe me that you can derive the same equation, but here you're going to have the sums of all ions on the surface and at infinity. This term remains the same. The density of all ions here is ions per meter cubed. Now this looks kind of complex and we want to simplify it. So if we take the right hand side And if we start expressing the right hand side, which you're going to do for homework, you can replace actually the concentration close to the walls with the Boltzmann relation between the concentration at infinity and the potential. So you're going to have sum of the concentration of infinity times this exponential term minus the concentration at infinity. It's still more complex than we would like it to be. So we can take the first three terms in the expansion for the exponent. We can redo all those sums here, and finally we end up that this difference in the ionic concentration here can be expressed with this term. Now, I had a question here which is kind of like just unless somebody answers immediately, then you're going to have this for homework. What happens with this term here? How does this term disappear? And why? So this one cancels because the sum of all ions times 1 minus the sum of all ions is cancels. This term remains here in the final expression. Now what happens with the first order term here? That's for homework. For now you believe me that it cancels. And we end up with this very simple expression, which is the equivalent of the expression which we derived before for the relation between surface charge and field. But here we have introduced a parameter which is called kappa, which is the sum of the ionic densities times the squared. So for each ions, you have the concentration of the ions times the squared electric charge, which is just a constant, times the charge of the ions squared, divided by epsilon 0 kT. You have to take the square root. And this new parameter, which is extremely important, which is the second major thing that you have to remember from this lecture, has a dimension of inverse length. Anybody has an idea how this parameter is called?
Debye.
Yeah, okay. I mean, certainly. This is the derivation of an important parameter which is called Debye length. What can happen with the Debye length? Well, we can take the alternative equation where we have the derivative of the potential here. So instead of using this form, which has surface charge, we use the other form which has the first derivative of the potential. We can put in the expression for the difference in the ionic concentrations at the wall and at infinity, the simplified expression which we derived the previous time. We can integrate this differential equation, which we're also going to do for homework because it's simple. And we obtain this formula which relates the potential at any point to the potential on the surface and an exponent of the distance which also has this constant inside it. So what I have done on the next slide, what you're so happy about, Brian? Okay. Okay. So on the next slide, I mean, if you think that you have gotten it, like on the next slide, you can immediately see what happens here. We have derived two expressions. I have plotted this in terms of 1 over kappa, which has a distance of length. This is the so-called famous Debye length. And you can see the importance of the Debye length. You have a surface. The relation between the surface charge and the surface potential is dependent on the Debye length. You want to understand how the potential decreases with distance. The relation between the decrease of the potential, the decay length in this exponential expression is also the Debye length. So the Debye length is actually going to give you, the characteristic decay length in terms of exponential decay. Now, you have three systems here with three different Debye lengths. The system with the the smallest Debye length actually has fastest decay of the potential. Now, what does the Debye length relate to? It relates to electrolyte concentration. So it gives you how the electrolyte concentration affects the potential and the ionic distribution in colloidal systems. This is the parameter which immediately tells you at this electrolyte concentration you are going to have this Debye length, so your electrostatic potential is going to decay this fast. Or your surface charge is going to be this depending on the potential, or vice versa. So this is a major estimator. You can also say, and people use this routinely, that the Debye length is going to also give you how far the potential actually spreads out. A Debye length of 10, for example, tells 10 nanometers, tells you that the electrostatic interactions are going to be important over a length of 10 nanometers. So you can only just calculate the Debye length, and you can say, well, I don't care about the electrostatic interactions in all their details. All I care about is that I know that they're going to be important for a distance of 10 nanometers or so. Now, fast, kind of quickest thinking question. Now, which of those Debye lengths is at higher electrolyte concentration? Which one? The left one. True. The higher the electrolyte concentration, the smaller the Debye length. Which tells you that when you add more electrolyte, you suppress the electrostatic interactions in the system. You have so many ions that they immediately absorb on the surface and the electrostatics just get suppressed. And this can be immediately seen. This is the last slide for today. You can actually, these formulas are fairly complex and you have actually to use them at least once in your homework. But good people have done just, this is not an approximation. This is just plugging all parameters with the exception of the concentration. So you can have this because the Debye length depends also on the ionic charge. So for electrolytes with different charges, you have different formulas. The point is that if you have one-to-one single charge electrolyte, you can calculate the Debye length in nanometers just by putting in the electrolyte concentration in moles. This is for electrolytes like calcium chloride, 2 to 1, 2 to 2, and so on. You can see that actually the charge decreases the Debye length a lot. And these are some specific values for the Debye length calculated for different electrolytes. So this is very important. This gives you how far the electrostatic interactions are going to be important in different electrolytes. Now you have 1 molar electrolyte. 1 over kappa, 1 over the Debye length is equal to 0.3 nanometer. Now how important is that? Is it important or not? 0.3 nanometers, if you remember, it's about the distance between the molecules in a solid body. So in this case, the Debye length is so small that all electrostatic interactions decay within 1 molecular distance. So if you put in 1 molar of electrolyte, you have essentially a system which doesn't care about electrostatics. And all van der Waals forces are going to be kind of freely taking their time and precipitating it and so on. If you take 0.1 molar electrolyte, which is about the concentration in human blood, you see that the Debye length already becomes much longer than the molecular diameter. It's not that long to be very important, but on a short distance it's important. So it allows biomolecules to separate each other, but it doesn't make them stay too far away from each other, otherwise our bodies would be too diluted, which happens if you drink too much water. I mean, you swell. One of the reasons for that. One of the reasons for that would be essentially all those osmotic effects which are related to electrostatics. Okay, now we go to a more typical electrolyte concentration, 10 to the minus third moles. You have a distance of 10 nanometers, and that's already a lot. And if you can do a pure water, you have a distance of the Debye length of 960 nanometers, 1 micrometer. Now, going back to the first slide, if you remember, what was the difference between all those particles? It was on the micrometer range. So the point here is that if you have very special conditions, you can do that. Now, however, the ones of you who are writing their papers in colloid science, don't put in a Debye length if you just took pure water from the tap and you did your research in this pure water. Don't estimate the Debye length to be 960 nanometers, which I have routinely seen in papers that I have to review. Now, I return these papers with the kind of like the idea that this is wrong, because you can take water from the tap and you won't expect it to be like exactly so highly deionized. Water in typical air environment is going to absorb carbon dioxide, so the electrolyte concentration is going to be much, much larger. So if you don't know how much the electrolyte concentration is, don't assume that it's pure water. So that's it. This is the final slide. Any questions about the Debye lengths or about the lecture in general? We have learned all the formulas that we need. Next time, we're going to use these formulas and calculate electrostatic repulsion between particles. From here on, it's very simple.
Is this lecture on the test?
No. The test covers everything, including last Thursday, but without this lecture. So you'll have time to think about electrostatics interactions a bit later. Okay, thanks then. Let's finish.